5 minutes ago, in a lab cooled colder than the empty space between galaxies, a chip smaller than the palm of your hand finished a calculation that should not have been possible to finish at all. Not slowly, not eventually. Not possible. Full stop. Using every computer humanity has ever built, running together, since the beginning of recorded history. And yet it happened. It happened. Quietly, without sirens or headlines scrolling across a newsroom screen, inside a Google facility where a machine called Willow sat at the center of a result so strange that the man who built it has spent the better part of 2 years trying to explain it to a public that mostly is not sure whether to believe him. This is not science fiction. This is not a trailer for a movie about parallel timelines. This is a real, peer-reviewed, published result, sitting inside a piece of hardware you could hold in one hand, and it is forcing some of the most respected physicists alive to ask a question that used to belong entirely to philosophy. Where, physically, did that computation actually happen? Because it did not happen only inside the chip. There was not enough room in there for it to happen only inside the chip. And once you understand why, the phrase "stop the world" stops sounding like clickbait and starts sounding like an honest description of what just occurred. Here is the number that started all of this. Willow completed a benchmark calculation in under 5 minutes that the fastest supercomputer currently operating on Earth would need roughly 10 septillion years to complete. 10 septillion is a 1 followed by 25 zeros. It is not simply a large number in the way a national budget is a large number, or the way the distance to a far-off The universe itself is roughly 14 billion years old. If you took every computer ever built by every person who has ever lived, wired them together, and let them run non-stop from the moment the universe began until this exact second, none of them, combined, would have finished the calculation Willow finished before your coffee had time to go cold. That comparison is not a metaphor. It is the literal published claim, verified through peer review, printed in the journal Nature. This already happened once. Before, back in 2019, when an earlier Google chip called Sycamore produced a smaller version of the same kind of gap. At the time, plenty of serious researchers assumed that classical computers running cleverer algorithms would eventually close that distance, and for a while they actually did narrow it. That is precisely why so many scientists remained cautious rather than declaring victory. Willow's result, several hardware generations later, did something different. It did not narrow the gap. It widened it into an entirely separate category. This is no longer two technologies racing on the same track and slowly separating. This looks like two different kinds of computation that were never running the same race to begin with. To understand why that gap exists, you have to understand what makes a quantum chip fundamentally unlike the laptop or phone sitting near you right now. A normal computer, no matter how fast, works through a problem one deliberate step at a time, tracing a single path from question to answer, the same way a person solves long division by hand, one line after another, no matter how quickly the pencil moves. A quantum computer does not work that way. Instead of bits that are strictly a 0 or strictly a 1, it uses qubits, and a qubit can exist in a blend of both states simultaneously, a property physicists call superposition. On its own, that already lets a quantum system represent many possibilities at the same time instead of one after another. But the real power only shows up once qubits become entangled with each other, linked in a way where changing the state of one instantly affects the state of another, no matter how far apart they sit inside the chip. Once that happens, the number of possible states the system can represent does not simply double or triple. It explodes exponentially, faster than intuition can track. By the time a chip reaches around 100 qubits, which is almost exactly where Willow sits with its 105 qubits, the number of distinct states it can represent is larger than the total number of atoms in the observable universe. Read that again slowly. A device that fits on a lab bench is working with more possible configurations than there are atoms in every star, every planet, every galaxy, and every speck of dust across the entire visible cosmos combined. And that is exactly where the uncomfortable question begins. A classical computer does its work using the physical hardware sitting directly in front of you, transistors flipping on and off inside a chip you could point to with your finger. If a quantum chip is genuinely juggling more possible states than there are atoms available anywhere in the observable universe to represent them, then where, physically, is that work actually taking place? It cannot be happening entirely inside the chip, because the chip is made of a finite countable number of atoms, and that number falls catastrophically short of what the calculation appears to require. That is not a rhetorical trick. That is the literal physical bottleneck that some of the most senior people in this field have been sitting with for years. And it is not a question that engineers trained purely in circuit design are equipped to answer alone, because the moment you ask it seriously, you have left electrical engineering behind and walk directly into the foundations of physics itself. For decades, there has been a controversial but seriously studied idea inside quantum theory called the many worlds interpretation, first proposed by the physicist Hugh Everett in the 1950s, and later expanded by thinkers, including David Deutsch. The idea is that a quantum event does not produce a single outcome. It produces every possible outcome, each one unfolding in its own separate branch of reality. Most people first encounter this concept through science fiction, time travel films, or comic book multiverses, but a meaningful number of serious physicists, including several who have spent entire careers on the mathematical foundations of quantum computing, take it seriously as a genuine candidate explanation for what is physically happening underneath. The equations, not merely a fun thought experiment for a late-night conversation. It is one of several competing interpretations of quantum mechanics that all make identical experimental predictions while disagreeing sharply about what is actually occurring beneath those predictions, which is a large part of why this argument has never been settled by evidence alone and may never be. Under the many worlds interpretation specifically, a quantum computer's advantage would not come from doing all of its work inside one single reality. It would come from effectively spreading the workload of a calculation across an enormous number of parallel branches at once, then somehow gathering the results back into the single answer that appears on the screen in front of you. Hartmut Neven, the founder and lead of Google Quantum AI, leaned directly into this explanation when Willow was first unveiled. He wrote that the chip's performance on this benchmark was so extraordinary that it lent credence to the idea that the calculation had, in effect, borrowed computation from parallel universes, and that this result supports the notion that we live inside a broader multiverse, an idea he explicitly traced back to Deutsch's earlier theoretical work. That is an extraordinarily bold claim for the head of a major technology company's quantum division to put his name on publicly, and it did not go unanswered. Critics pointed out that the specific benchmark Willow used, called random circuit sampling, was engineered from the ground up to be difficult for classical computers and easy for quantum ones, essentially a demonstration purpose-built to showcase quantum advantage rather than a broadly useful real-world calculation. Because Google itself designed and controls this benchmark, a number of scientists argued it should not be treated as the strongest possible evidence for something as enormous as proving the existence of parallel universes, and that simpler explanations, rooted entirely inside standard quantum mechanics, can account for the same numbers. Some observers also noted, fairly, that a company under intense competitive pressure has an obvious incentive to frame its results in the most attention-grabbing way available, which does not make the underlying physics wrong, but is worth remembering. What almost everyone in the field agrees on is that the RA, or computational result itself, is real, independently verified, and extraordinary. What remains fiercely contested is what that result implies about the deeper structure of reality. Whichever interpretation eventually wins, quantum computers rely on something strange even under the most conservative single-universe reading of quantum mechanics, a phenomenon called interference. Different possible quantum states inside the system interact with each other while the calculation runs, reinforcing the paths that lead toward correct answers and effectively canceling out the paths that lead toward wrong ones in a process that has no real equivalent anywhere in classical computing. That interference is, in a very concrete sense, how the machine lands on a correct answer at all instead of producing pure noise. Designing a good quantum algorithm essentially means engineering it so that wrong answers cancel each other out as completely as possible, while the correct answer gets reinforced again and again across the run of the calculation. Under the many worlds framework, that interference gets interpreted as a limited overlap between separate branches of reality, not communication in any conventional sense, and certainly nothing resembling a message passed back and forth, but some deeper form of shared computation bleeding across branches just enough to influence a final result. Willow does not prove any of that. It does not open a doorway. Nobody on the research team is claiming it sends or receives a signal from anywhere else, or that a person could ever step through into one of these other branches, even if they genuinely exist. What it does is place a real, unresolved question about the foundations of physics directly in front of a working piece of hardware you can hold in your hand, instead of leaving it as an abstract argument confined to journals and seminar rooms, full of theorists debating points that, until very recently, had no obvious connection to anything a person could actually build and test on a lab bench. Theory that quantum computing might genuinely scale towards something practical instead of remaining permanently stuck as an impressive but limited lab demonstration. And this is exactly where most casual coverage of Willow stopped paying attention, even though the real research never slowed down. Through 2025 and deep into 2026, Google kept building on the same underlying architecture. In April of 2026, the company announced what it described as the first demonstration of verifiable quantum advantage on Willow-class hardware, a milestone explicitly framed as a step toward genuinely useful computation rather than another narrow benchmark result. The distinction matters enormously to people inside the field, because a raw speed benchmark like random circuit sampling is one thing, but a result that can be independently checked by outside parties, confirming the system actually did what it claimed, is a meaningfully higher bar to clear. Around the same period, Google widened access to the platform, opening it to outside research partners through an early access program, with a submission deadline in May of 2026 and selected teams notified by July 1st of this year. Access was also extended to researchers in the United Kingdom through a national quantum computing partnership, a clear move toward getting more of the scientific community actually running experiments on the hardware instead of simply reading about it from a distance. In July of 2026, just weeks ago, Google published another result that received far less attention than the multiverse headline, but may matter just as much long term. Their team demonstrated a reinforcement learning system that lets the Willow processor continuously learn from its own errors while it runs, stabilizing itself against environmental drift in real time, rather than requiring engineers to manually recalibrate it between runs. In testing, that system made the chip's logical error rate roughly 3.5 times more stable under artificially introduced hardware drift, and cut the error rate itself by around 20% compared to conventional recalibration. In plain terms, the machine is starting to learn how to keep itself steady, the same way a tightrope walker learns to make constant tiny corrections without consciously thinking through each one. Google also began hedging its bets on the underlying hardware itself. In March of 2026, the company announced it was adding a second, entirely different kind of quantum hardware built on neutral atoms, running alongside its existing superconducting approach, since nobody in the field is certain yet which physical platform will ultimately scale best toward a truly large, fault-tolerant machine. Google has laid out a 6-stage roadmap toward that goal, and Willow represents only the second milestone on it, roughly 100 qubits with early-stage error correction working as theory predicted. Key next milestones involve a long-lived logical qubit that can hold its state over much longer stretches of time, and eventually a working logical gate between two separate logical qubits, both necessary steps toward a machine capable of running the kind of extended calculations that would matter for drug discovery or materials science, rather than a single benchmark designed to grab headlines. As of mid-2026, Google has not yet published either of those next two milestones and has been careful not to attach a firm timeline to when they might land. Google is also no longer working alone at the top of this field. IBM has been pushing its own hardware hard, including a newer 120-qubit chip called Nighthawk, explicitly aimed at reaching practical quantum advantage on real-world problems before the end of this year. National research program, as across China, Canada, Germany, and Japan, continue investing heavily in their own quantum efforts, each pursuing a different underlying approach, from trapped ions to photonic systems built around particles of light rather than superconducting circuits. Venture funding into quantum startups has climbed sharply through 2025 and into 2026, all as investors who once treated the field as a distant speculative bet now treat it as a genuine near-term race. None of these competing efforts have yet matched Willow's specific below-threshold error correction results on published, peer-reviewed hardware, but the overall race has clearly accelerated since Willow's debut. Most security researchers still place the point where quantum computers threaten today's encryption, sometimes nicknamed Q-Day, out toward the early 2030s rather than tomorrow, meaning Willow and its rivals represent real, measurable progress rather than the overnight arrival of a world-altering machine. That distinction matters because it is very easy for coverage of this technology to slide from genuinely impressive scientific progress into breathless claims that outrun what has actually been demonstrated. And separating the two requires paying close attention to exactly which milestone has been peer-reviewed and confirmed, versus which one is still sitting on a roadmap slide as an aspiration for some future year. Even with that caution firmly in place, it is worth sitting with just how strange the underlying physics genuinely is, because you do not need to accept the multiverse explanation to find this story unsettling in a good way. A classical computer is fundamentally a machine of certainty. It takes a defined input, follows a defined set of steps, and produces a defined output every time, in a way you could in principle trace by hand if you had enough patience and enough paper. A quantum computer is built on top of genuine uncertainty at the deepest level physics currently understands, and rather than trying to eliminate that uncertainty the way engineers usually try to eliminate noise from a system, it deliberately exploits that uncertainty as the core resource that makes the whole machine work in the first place. Humanity has been here before, in a different form. People used fire long before anyone understood the chemistry of combustion happening inside it. Electricity was harnessed and put to work in wires and motors well before anyone had a complete theory explaining what was happening at the level of individual electrons moving through a conductor. In each case, practical use arrived well ahead of full theoretical understanding, and society adapted to the technology long before the textbooks caught up with a clean explanation of why it actually worked. Quantum computing may be following that same pattern once again, except this time the underlying phenomenon being harnessed is something as fundamental and strange as superposition, entanglement, and interference, properties of reality that some serious physicists genuinely believe may only make complete sense if our observable universe is not the only one that exists. Willow does not prove the multiverse is real, and it would be inaccurate and misleading to present that as settled fact, no matter how compelling the framing sounds in a headline. What it does do is take an idea that spent decades sitting almost entirely inside theoretical physics papers, argued over in seminar rooms most people will never enter, and force it into a very concrete, very public conversation involving an actual working device that fits on a lab bench, cooled to temperatures colder than deep space, built by engineers, and capable of producing results that a growing number of serious scientists genuinely struggle to explain using conventional single-universe physics alone. Throughout history, humanity has kept expanding its understanding of reality by building better instruments rather than by pure thought alone. The telescope showed us that Earth was not the center of everything, dethroning centuries of assumption almost overnight, once Galileo pointed a lens at the sky. The microscope revealed entire hidden worlds inside a single drop of water. Worlds nobody had reason to suspect existed until someone built a tool capable of showing them. Particle accelerators showed us that solid matter is, at bottom, mostly empty space, animated by invisible forces holding it together. Quantum computers like Willow may be pointing towards something equally disruptive to our intuitions. The possibility that reality itself may not be a single unfolding timeline, but something closer to an enormous branching structure, with our current moment representing just one thread inside something vastly larger than anything we have previously had the tools to detect. So, the next time someone tells you quantum computing is simply about building faster processors for the same old kinds of problems, it is worth remembering what actually sits underneath a chip like Willow. This is not simply an engineering story about smaller transistors or clever new algorithms layered on top of familiar physics. It is a story about a machine whose entire method of operation seems to strain against the physical limits of a single observable universe, built by a team whose own lead scientist has publicly argued, in writing, that the most coherent explanation available involves borrowing computational power from realities beyond our own, a claim that remains genuinely contested rather than confirmed by the wider scientific community. Whether that particular claim eventually holds up under the weight of further evidence gets replaced by a more conventional explanation grounded entirely in standard quantum theory, or simply remains an open question for decades to come, one thing is already certain. 5 minutes ago, somewhere in a lab colder than deep space, a chip that fits in the palm of your hand finished. The calculation the rest of the universe's computers, combined, could never have finished at all. The line between cutting-edge engineering and the deepest open questions in fundamental physics has never been thinner than it is right now,